Okay, Steffi, are you there in the last class?
Yes, ma'am.
Can you tell me the definition of the pseudo order reaction?
Ma'am, only half I was there.
Not in the beginning, right?
No, ma'am.
Okay. Michael, can you tell me pseudo order reaction?
Appear to be of high order but actually show lower order kinetics.
Okay. That is known as pseudo order reaction, right? Then what is Arrhenius equation? Sharon not there, right? Nandana, you can tell me.
K is equal to AE raised to minus of EA by RT.
Yes. What is this EA? Naureen? EA.
Activation energy,
Can you define this activation energy?
the energy needed to form intermediate.
Yeah, intermediate or the activated complex is known as activated energy, right? Yes. Then now we can discuss another graph that's showing that plotted against kinetic energy and fraction of molecules. Have you finished this one, right? In the last class? Activation energy, these points. Yes. Okay, another graph that plotted fraction of molecules against this kinetic energy. Fraction of molecules is plotted against kinetic energy. What do you mean by this fraction of molecules? Fraction of molecules. We can also write this fraction of molecules as Ne by Nt. Ne stands for the number of molecules with energy E. Okay, number of molecules with energy E divided by Nt stands for number of molecules, number of total number of molecules. Okay, total number of molecules. Instead of fraction of molecules, we can also write Ne by Nt. Number of molecules with energy E, then total number of molecules. It is plotted against kinetic energy. And in this graph, you can clearly see that there is one maximum, right? And this is considered as the most probable kinetic energy. That means all these molecules do not have the same kinetic energy. Okay? All the molecules in that reactant species, they do not have the same kinetic energy. This most probable kinetic energy, that's the energy that's showed by maximum number of molecules. Clear? So along with this graph, first of all you can draw this graph. And along with fraction of molecules, you can write this Ne by Nt in the bracket. Distribution curve showing energies among gaseous molecules. Finished?
No.
Okay, then you can complete it.
Okay, ma'am.
Yes. Then you can write the points here. All the molecules in the reacting species do not have the same energy. Do not have the same energy. Then the peak of the curve corresponds to most probable kinetic energy that is the kinetic energy of maximum number of molecules. You can see one maximum in that graph, right? That's the peak of curve corresponds to most probable kinetic energy. That is the kinetic energy of maximum number of molecules. And there will be decreasing. There are decreasing number of molecules. With higher and lower energy. These are the main points that can be obtained from the previous graph. Okay, all the molecules in the reacting species do not have the same energy, and the peak of curve corresponds to most probable kinetic energy, that is the kinetic energy of maximum number of molecules. And there are decreasing number of molecules with higher and lower energy than this value. Okay. Dia, can you read the points?
All of the molecules in the reacting species do not have the same energy. The peak of the curve corresponds to most probable kinetic energy, that is, kinetic energy of maximum number of
Yes.
molecules. There are decreasing number of molecules with higher and lower energy than this value.
Yes. Have you completed, children? Okay, then you can again look at this graph. In this graph, you can clearly see that here this maximum number of molecules, right? So here, compared to the lower value or higher value, here the maximum number of molecules with this kinetic energy. That is described in the second point. There is decreasing number of molecules with higher or lower value than the most probable kinetic energy. And we can also state this fraction of molecules Ne by Nt. Ne is number of molecules with energy E, and Nt, that is the total number of molecules. Is this clear? Any doubt, children? Anyone? Shall I move to next one? Then we are moving to the next graph with increasing temperature. Okay. So before moving to this graph, you can note down this point. Increasing the temperature of the substance increases the fraction of molecules. We have learned that all the molecules do not have the same energy, right? But when we increase the temperature of the substance, it will increases the fraction of molecules which collide with energies greater than activation energy. That means the molecules that comes under the most probable kinetic energy, it will increases. Increasing the temperature of the substance increases the fraction of molecules which collide with energies greater than activation energy. That will be easy for the formation of products. Okay, if there are more molecules which collide with energies greater than the activation energy, it will be easy to form the products. That's it. Meenakshi, can you read this point?
Increasing the temperature of the substance increases the fraction of molecules which collide with energies greater than the activation energy.
Yeah. Shall I move to next graph? Yes. This is also kinetic energy versus fraction of molecules. Okay, kinetic energy versus fraction of molecules. And this graph you can see two curves, right? One with temperature T and the other one with T plus 10. And compared to both these curves, you can see that this is the energy of activation. This is the limit. Okay, this is the limit. And here the number of molecules, the fraction of molecules that greater than activation energy, it increases, right? This one is the graph. So here the fraction of molecules increases, having the energy greater than activation energy. It is clear from the graph, the diagram, that in the curve at T plus 10. The second one is T plus 10. Okay. The area showing the fraction of molecules having energy equal to or greater than activation energy gets doubled, leading to doubling the rate of reaction. When you look at the first curve, that is depending on T, only lesser number of molecules are considered, right? Only this much portion is considered. And when the temperature is increased by 10 degree, it also increases. That means the fraction of molecules greater than or equal to this activation energy, it increases. This much portion is also added along with this. Okay? Is this clear now? It is clear from the diagram that in the curve at T plus 10, the area showing the fraction of molecules having energy equal to or greater than activation energy. This is the point of energy of activation or activation energy. So only need to consider the molecules after this energy of activation. Okay, we need to consider only this portion. In the first graph at T, only this much molecules is considered. At T plus 10, the number of molecules greater than or equal to activation energy, it increases. Clear? You can also plot it in the graph itself. This area shows the fraction of molecules reacting at T. This area shows the fraction of additional molecules which react at T plus 10. Okay, this is clear. Yeah, Chut, any doubt?
Is this graph there in the textbook?
Yes, figure 4.9, page number 114. Have you got it, Achut? Yes. Any doubt, children, in this portion? When the temperature increases by 10 degree, the fraction of molecules that have great value equal to this activation energy or greater than activation energy, it will be increases. Approximately gets doubled. Okay. So it will helps to doubling the rate of reaction. And you look at the curve, it also broaden, right? So along with this, you can write one more point. Have you completed this point, children?
No.
Okay. Then you can add one more point there. When temperature increases, curve moves to higher energy value and curve broadens. And this curve has one more name, that is Maxwell-Boltzmann distribution curve. Okay, Maxwell-Boltzmann distribution curve. That's the name of the scientist who discovered this relation of temperature with the rate of reaction. Sharon, can you tell me what all points can we obtain from this graph?
Temperature increases,
Yes.
curves move to higher energy value, and curve broadens.
Yes. Then what about the fraction of molecules? What happens to the fraction of molecules when temperature increases?
It doubles.
Which type of molecules double? What about their energy? Is it less than activation energy or greater than activation energy?
Greater than
Yes.
activation energy.
The fraction of molecules having energy equal to or greater than activation energy gets doubled. Then it will lead to the doubling of the rate of reaction. Okay. This is clear? And this curve also known as Maxwell-Boltzmann distribution curve. This is clear, children? Yes or no? All of you please switch on your videos. Shivani, which slide?
No, ma'am, nothing.
Yeah, which one?
No, ma'am.
Okay. So next we are going to derive an equation from this Arrhenius equation. Okay. Can you tell me the Arrhenius equation? Arrhenius equation. Lydia, can you tell me? Yes? Lydia, can you hear me?
Yes, ma'am.
Yes, tell me. What is Arrhenius equation?
K equal to AE raised to minus EA by RT.
Okay. And we know that A is Arrhenius factor, then E raised to minus EA by RT. EA is the activation energy, R is the universal gas constant, T is the temperature. Then you can also write E raised to minus EA by RT. It is considered as the fraction of molecules having activation energy. Okay. Sorry, fraction of molecules having this kinetic energy either equal to or greater than. Okay. Activation energy EA. E raised to minus EA by RT, it is considered as the fraction of molecules having kinetic energy equal to or less greater than activation energy. So you can write the symbol. So we are going to taking log on both sides of this equation. Number this equation as 1, taking log on both sides. Then it will become ln k is equal to this e raised to minus EA by RT. We will remove this exponential factor. Okay. Then it will become minus EA by RT plus ln A. Okay. ln k, that is equal to minus EA by RT. We will remove that exponential factor. In the bracket you can write on taking log we can remove exponential term. Do you remember that portion when you are taking anti-log on both sides? We will add this exponential term, right? And on adding this log on both sides, we can remove the exponential term. Okay. So this is the equation. Then we are considering two temperatures at temperature T1 and temperature T2. Okay, at temperature T1 and at temperature T2. Shall I move to next page, children? Have we completed? Achyut?
Yes, ma'am.
Yes. At temperature T1. How can we rewrite this equation? Shivani, can you tell me how can we rewrite this equation at temperature T1? Yes. Equation is ln k is equal to minus EA by RT plus ln A. So can you tell me? Shivani? Shivani, can you hear me? Vidur, can you tell me How can we rewrite this equation at temperature T1?
ln k
ln K1 is equal to, yes,
e minus ea
hmm,
by rt1
yes,
plus
hmm,
ln a.
yes. Then what about temperature T2? Meenakshi, can you tell me? At temperature T2.
K2 is equal to minus EA by RT2 plus LNA.
ln A. Okay. Then we are going to calculate the difference between ln K2 minus ln K1. K2 minus ln K1. It is minus EA by RT1 plus ln A minus of minus EA by RT2. Sorry, here it is T2, here it is T1. Okay. Then plus ln A. These two will be cancelled, right? Then we can write this equation. Here it is minus of minus, that means positive, right? So EA by R can be taken as common. Then it is 1 by T1 minus 1 by T2. Then ln K2 minus ln K1. How can we represent that? ln A minus ln B.
K2 by K1.
Yes, ln K2 by K1. Shall I move to next page, children? Yes or no?
Ma'am,
Yes. Any doubt?
the like last step, how did we get that?
Which one? This one, right?
Yes, ma'am.
In the previous equation, it is minus EA by RT2, right? This ln A and ln A, it's opposite sign, so it is cancelled. Okay. Then here it is minus of minus, so plus. Here it is minus. So we just take EA by R, it's a common term. So we write it outside the bracket. Then we will write this 1 by T1 because it's a positive term. It's first, then minus 1 by T2. Is it clear now, Achu? Yes. Okay, I will write one more step before this one, then it will be more clear. Minus EA by R, then it is minus of 1 by T2 plus 1 by T1. Then we just reverse this equation again. Okay. Shall I move to next page? It is ln K2 by K1 is equal to EA by R 1 by T1 minus 1 by T2. Just 1 minute. Okay. We can cross multiply here, right? T2 minus T1 divided by T1 T2. Then one more step, convert this natural logarithm to base form. So it will be log K2 by K1 is equal to EA divided by 2.303 R and T2 minus T1 divided by T1 T2. This is the okay. So I will write it again. This log K2 by K1 that is equal to EA by 2.303 R. Then it is T2 minus T1 divided by T1 T2. This is the final equation. K1, K2, they are the constant values. Rate constants. T1, T2, temperature. Have you finished? Okay. Then one more thing. We have learned this equation, right? ln k is equal to minus EA by RT plus ln A. Right? ln k is equal to minus EA by RT plus ln A. Can you tell me which equation is similar to that of this one? You already learned that. From which equation we can compare this one? Adul, can you tell me?
ln r is equal to minus kt plus ln r0.
I'm asking about the equation that you learned in mathematics. Equation of? Yes, equation of straight line, right? Y equal to mx plus c. So this equation can be also used to plot a graph. Okay. You can rewrite that equation, y equal to mx plus c, that is equal to ln k, that is equal to minus ea by rt plus ln a. Here you can plot it. Here it is 1 by t. And here ln k. The graph is like this, and here the slope gives the value minus ea by r. Okay, and the intercept ln a. Finished? All of you?
Yes, ma'am.
Yes. So that's about this portion. Then two more topics remaining in this chapter: effect of catalyst and collision theory of chemical reactions, that we can discuss in the next class. Okay. Do you have any doubt in this portion? Yes, from this Arrhenius equation, k equal to a into e raised to minus ea by rt, we just taking log on both sides. That is ln k is equal to, we just remove that exponential term, then minus ea by rt plus ln a. That's in the form of a straight line, equation of straight line, y equal to mx plus c. So from this equation we can directly write down the slope, that is m is equal to minus ea by r, and c, that is the intercept, ln a. Okay. Then at temperature T1 we can rewrite this equation, ln k1 is equal to minus ea by rt1 plus ln a. Then at temperature T2, ln k2 is equal to minus ea by rt2 plus ln a. Then we just find out the difference between these two values, ln k2 minus ln k1, that is equal to minus ea by rt2 plus ln a minus of ea by rt1 plus ln a. Then we just cancel ln a terms. Then that is equal to ea by r into 1 by t1 minus 1 by t2. Okay, then we convert this natural logarithm into base, and that will be equal to log k2 by k1 equal to ea by 2.303 r into t2 minus t1 by t1 t2. Then we just plot a graph related to this equation. This is clear? Any doubt? Any doubt, children? Nothing, right? Okay, just wait. Let me take your attendance. Okay, children, then we can discuss the remaining 2 topics in the next class. Okay. Okay, then thank you all. See you in the next class. Bye.
Thank you.
Thank you.